today is mostly Mars. And as you probably know, I know John has been following it very intensely. We've had a lot of things happening within the last week. And so it is only appropriate that we talk about Mars today. Okay, well, I got a confession to make. You know, when I agreed to do this talk way back when, I had no idea what was going to happen. And so in order to prepare, I prepared two talks. One was if the Perseverance was successful, and we could have a lot of stuff on there. But in case, you know, it crashed or something, didn't go away, I had to prepare something else for you guys, so I wouldn't be able to say to you, okay, sorry, it crashed, no talk today. But anyway, it was successful, so we will go on. Well, it was very successful. I would say, I would say 100% successful, but, you know, the engineers at NASA said, well, you know, it's 98% because one of the microphones, they had two microphones. One of the microphones didn't work on the descent stage, although it's working now. So, you know, talk about perfection. But other than that, everything seems to be doing very well.
Hey, George, do you
Yes.
have a light in front of you that you can turn on? Because you are a dark man.
I know, but the sun is behind me, unfortunately, and I have a double, I can show you my, let's see, for what it's worth. There, but even the light doesn't do much, does it? So sorry about that. I'm in the shadows.
George, have you tried the adjustment in video for enhancing likeness? If you go to video settings.
I tried. Yeah.
Oh, you tried it. Okay.
Yeah.
Low light.
We can do that later. But anyway, okay. The probe landed within 15 feet of a designated target. So, you know, imagine you're playing golf and you shoot a drive from New York and you want to hit a hole in one in Los Angeles golf course. I mean, that's basically what they're attempting to do. It collected videos and all the way down. They had 9 cameras, and you'll see some of the video clips as we go on the talk. Now, you remember, Mars is away. It's 100 and some million miles away. So it takes a little bit of time for speed of light to get there. 11 minutes to be exact at this point in time. So what does that mean? Everything has to be done remote control. Nothing can be done in, live, if you will. They did not know they had a success until 11 minutes after the craft landed.
Yeah. So they were all jumping and celebrating for an event that had happened 11 minutes ago.
No. They celebrated when they got the signal. In fact, they got the first image, which was, you know,
That's what I mean. It was 11 minutes ago.
Exactly. But, you know, it just tells you that to communicate now even, it's basically 22 minutes round trip. You send a signal and then you get a response, you know. And so it's a phenomenal computer science project to think that everything ahead of time had to be done. And more importantly, artificial intelligence plays a major role in this rover, because unlike previous ones, you know, you could go one step at a time. So what they did is they had an image of land before, sent it back to Earth, decided which path the rover was going to go, and so they moved it like 3 feet or 5 feet, and then signal back where they are. So imagine, you know, doing it. Now AI is programming the rover, and so they don't have to do it as controlled as they did with Curiosity, which is a major upgrade. Okay, let's, I have a lot of videos, so I hope you guys brought popcorn.
Hey, George, one question before you start the videos. Are all these, how many of these videos are simulations versus real time?
This is all real. This is all real.
All real.
Well, all real until later on when we talk about things that were planned. That's not real. But these are all real. This is a camera that's on the bottom of the rover, and you can see it moving around. And at some point it starts jiggling because the parachute came out.
Yeah, that's the heat shield that came off.
Yeah, the heat shield. Well, but also the parachute. First the heat shield first, and then the parachute.
So this is a photograph from the unit that actually landed, as opposed to the, was there a mothership or something?
Correct. This is the camera on the bottom of the rover as it's descending. As it's descending.
Wow. Now, are there rockets that are controlling any of this as they're going down?
Yes, it's when they let go of the parachute. I have a diagram that I will show you.
Okay.
Okay. And now it's getting very close, and you start seeing dust because the rockets are blowing, down to keep the unit up.
So is the Perseverance deciding by looking where to land?
Yes.
So it's making decisions based upon what it's seeing.
Yeah, exactly. Now the dust starts. There, now it's landed. No, not yet.
Sure, we'll hear the Martians applauding.
Yeah. Okay.
Okay, so this is a view from the bottom of the of Perseverance itself, not the unit that was carrying it.
Correct. Correct. Now here's a diagram basically of what went on, and you see here there are a bunch of stages that let's see if I can get my pointer. The cruise stage separation occurred 10 minutes before landing. And so you had that got dropped off. The heat shield is in front as the thing is coming down. And it's coming down. And at a certain point where it starts leveling off, starts leveling off when the parachute pops open. And then the heat shield drops off. And then you have the crane. Remember, the way it landed is it has a crane, and it lowered the rover down because the rover couldn't be too close to the rockets that are keeping the thing afloat. Then they get rid of the parachute. They drop the rover, and now you have it. The rockets carrying the rover, it drops it down, cuts the umbilical cord, the rockets go away, fly away, and the rover is down on the ground. So the whole thing, 10 minutes, but since it takes 11 minutes for signal, they really didn't know what was going on until it reached the point. Now, this is a video of the engineer, Al Young, who describes the descent.
So let's start with the parachute upload camera, and let me give you a quick warning to not blink, because things go really fast here. You can see that you can get a sense really of how violent that parachute deploy and inflation are. The parachute pack, is packed so densely that the pack is basically the same density as oak, and it's about 150 pounds. It gets launched out of the spacecraft with a mortar, which is basically a cannon, with a muzzle velocity of around 100 miles an hour. And the spacecraft itself was going about 1,000 miles an hour at this point, going about 1.75 times the speed of sound. So just in case you blink, let's show you that one more time. Kind of see that in high speed and then or real time, and then we'll slow it down and take a look at the details. Okay, so let's try to walk through this a bit slower, this time at about quarter speed, and we'll pause at times to point out things we see. So let's start that rolling. Okay, here you can see the pack getting pushed out of there. You can kind of see the pack right in the middle as it's being pushed, and the parachute lid, which is right on top of it, it's kind of that circle to the left of the pack, was on top of the pack. It was there to protect the parachute during entry. It's got some thermal protection system material on it to keep the parachute nice and cool and protected. And the pack is used to push that lid right off the vehicle, given that cannon force. You can also see some of the other things that have popped off of that lid, which is kind of expected given how violent this launch really is. So let's move on from here. So we keep going out here. You can see the pack reach what we call line stretch. So that's as far as it's going to go. It's where the parachute's going to start inflating. That's about 150 feet behind the spacecraft, and it got there in just under 1 second. So this pack is really moving. That's pretty much, as the parachute starts to come out, you can see the pack is rotated about 90 degrees. That's pretty common. We've seen that in some of our testing here on Earth at high altitude as well. So let's keep going and take a look at the inflation. So that inflation really looks textbook. It's nice and symmetric. The parachute opens in only about 7/10 of a second, again, really fast. There's no evidence of tangling of the lines, which is great. There's about 2 miles of lines in the parachute system. So the fact that we don't see any evidence of tangling or any kind of other misbehavior is great news. And I'm sure we'll be studying this video for many, many years and picking it apart frame by frame. And of course, we have a second camera on board as well that recorded this launch and inflation of the parachute. You might notice the pattern that's on the parachute here. Distinct patterns are useful in helping us determine the clocking or orientation of the parachute. Also, the contrasting sections can be useful in tracking different positions of the parachute, different portions of the parachute as it inflates. So it's especially useful when we have multiple cameras, as we do here, and are trying to track features in the parachute inflating. In addition to enabling incredible science, we hope our efforts and our engineering can inspire others. Sometimes we leave messages in our work for others to find for that purpose. So we invite you all to give it a shot and show your work. Let's move on to the Rover downloop camera and take a look at that in a little bit more detail. So if we start that up, you can see the heat shield falling away very nicely and symmetrically. Pausing here, we can take a look at what we see on the heat shield. First, we see the medley components on the heat shield. You can see the electronics box and the gold wires that lead to all the various sensors that measure the aerodynamics and heating during the entry portion of flight. We can also see some white flecks in different places, both on the heat shield and free flying, which are likely frost that accumulated on the heat shield. That heat shield is really, really cold during cruise, so it's not at all unexpected to see some of that frost appearing on the heat shield on the inside. You can also see something we didn't expect to see if you kind of look at the 4 o'clock position on the heat shield or so, towards the middle, somewhere between the middle and the edge. One of the springs that helped push the heat shield off seems to have come loose. It doesn't, it's not much of a big deal, but it's definitely not what we expected. If you look at the other 8 springs, they actually are where they're supposed to be, all around the edge of the heat shield. There's no danger to the spacecraft here, but it's something we didn't expect and something we wouldn't have seen if we didn't have the camera system to show us what was going on. So let's keep rolling here. We can see that the heat shield basically stays in the same orientation as it flies away from us. They'll come back into view in a little bit. But this is great. This is kind of what we expected in terms of the aerodynamics of that heat shield. It doesn't tumble or do something weird that was unexpected in flight. So that's very useful to have this video to show us that. So in the interest of time, let's skip ahead to about 15 seconds before backshell separation. So starting this video here, you can see that the spacecraft is rocking back and forth while hanging under the parachute. This rocking is less than it was earlier in flight, but pretty much what we expect. There, that white flash was backshell separation, and you can see us throttle up and begin our divert maneuver. You can see the vehicle's turned over, so we're actually beginning to fly east. And that's why you can see the delta over there. As it maneuvers eastward to the eventual landing site, it actually passes over the field of view, will pass over the landing site and then kind of overshoot it a little bit because it's got to stop that horizontal divert that we did. You can see everything's nice and smooth now that the engines are under control, that on-sheet parachute rocking is gone. So here we are, slowing down and stopping, and we're coming straight down on our eventual landing site here. You can see that as we really begin to slow down here, you can see the engines as we get lower throttle up there and stop us here, and you can see it beginning to push all that dust around on the ground on the two sides. That shaking there is the rover deploying and the mobility during sky crane. And here we are coming down, and that rocking motion of the rover we'll see in other videos. But that settles down right before we hit the ground in a nice, safe, flat spot. There doesn't appear to be too much of concern that's right below us. So that was the rover's view looking down. Let's take a look at the descent stage view looking down as well during that sky crane portion of flight. So here we go. The rover begins to drop away from the descent stage, and that's the first part of mobility deployed. You can kind of see here right before we pause that the mobility kind of shook a little bit in that first deployment. Here you can see the bridles that are hanging down from the top of the picture. Those are what's supporting the weight of the rover below the descent stage. And if you look down toward the left, the bottom part of the image and toward the left, you can see that gold umbilical. That's what's transferring all the information between the rover and the descent stage, including this video. This picture is coming down from the camera up on the descent stage down to the rover through that cord, in addition to other information that's going back and forth. So as we keep going here, you can see the bogie.
I've never been on the phone. I'm at my meeting.
Back, you see those wheels, the back two wheels on either side swing down. That caused a little bit of rocking of the rover as expected, but you can kind of see that kind of settles out a little bit right as we enter that plume and dust cloud as we get down and touch down. And the video ends at touchdown, of course, because the camera that's taking this video is about to leave this area in a hurry on that descent stage after we cut it loose from the rover. So now let's take a look at the rover upload camera. So now staring up at the descent stage from the rover. So here we go. We got a really close-up look at the descent stage, and we can start rolling that. You can see the descent stage as the rover begins to fall away from it, and see the effect of that rover wobble from the mobility deploy. So pausing here, the first thing that most people will probably notice is that there's no plumes or no visible smoke or anything else coming out of the rockets at the corner of the descent stage. That's expected. Hydrazine isn't a combustion reaction when we burn it. The exhaust products are nitrogen and hydrogen, which are clear. So we expect the plumes to be clear. That's what we see in tests here on Earth as well. So I can promise you those engines are on, though. One thing you can see in the Earth testing we do is that the thrust chambers of those engines get kind of hot and glow pink. And you can kind of see that in the engines here, especially if you look at the engine at the very top right of this image. If you look closely right above the engine bell there on the thrust chamber, you can see little streaks of pink on there. And that's what's happening. As the engines have been on for a long time, they get really hot. And that heat shows up there in those pink stripes that we see. So take a look at that closely when you get a chance to look at the image in some detail. As with the previous videos, you can see the bridles that are supporting the weight of the rover there at the bottom now of this image, and that umbilical, again, transferring data back and forth between the descent stage and the rover. So let's keep going a little bit more. You'll see the image begin to wobble a little bit here. I can promise you it's not the descent stage wobbling, it's actually that rover tipping back and forth a little bit as we saw as the mobility deploys, both the first initial mobility deploy and then the bogies deploying. As we near touchdown, let's slow it down a bit and proceed in slow-mo here. So now we're watching about quarter speed. Things are getting pretty dusty here as we get down toward the bottom. Take a look here at the bottom left of this picture. You'll see actually the instant that we cut the descent stage away. And you'll see those bridles begin to get retracted up toward that descent stage as they're pulled up. And this is as planned. There they go. See as they got yanked up there right before. And then we'll see the descent stage begin to turn and ascend and head out toward the northwest with the umbilical dangling behind it. Since the rover was pointed almost directly to southeast, the descent stage chose to go toward the back. That's also to make sure, of course, that the engines don't plume the rover, that we don't damage the rover with that engine thrust. So we sent that descent stage off to the northwest, which Jessica will show you about in a little bit. So I can and have watched those videos for hours and keep seeing new stuff every time. So I invite you all to do that too.
Now, this is a nice, it's part of a 2-hour news report from NASA. So if you're interested in, you can probably see the whole 2 hours. They go into lots of detail. Okay. You know, remember we have the rover and all the stages, but above on the skies, there is monitoring. We have like, I think 6 orbital satellites going around Mars all the time. And here's a photo from one of the orbitals showing the landing, and you can see the the highlight there is a parachute. So we had a number of places where we could monitor what's going on. And I would say Mars is probably as well looked at almost as Earth. We know, as you know, different features and things like that based on the orbiters that have been going up, and they've been flying like for the last 20 years. Okay, let's see. I don't want to do that. Okay. I need to go back. Okay. This is a twin. NASA does everything in duplicate. And the reason for this is in case something goes wrong or unexpected on Mars, they try to duplicate what's, you know, here on Earth, what happened on Mars to fix things. For example, as wheels get eroded or some camera malfunctions, they try to duplicate it on Earth with a duplicate copy of the rover. So this is Perseverance 2, a clone of what is on Mars right now. These are just snapshots, which you've seen before. Now, I was interested, you know, they used 3 ropes to hang I would have thought that I would have used 4, but I guess 3 will do the job. But in case one of the 3 fails, it seems like you're asking for a catastrophe. So my suggestion is, you know, they should really have 4 and the umbilical cord. This is the first snapshot of the ground that the rover made upon landing and when the dust settled. And they, you know, took a selfie. So here's the wheel of one of the wheels of the rover and the ground around where they landed. Now, one of the things that this Curiosity, Perseverance has another, I guess, flying rover. It's called Ingenuity. It's a small helicopter that was designed to act as a scout as Perseverance starts traveling. Unfortunately, we're not going to see anything with Ingenuity until April, because there are, you know, now they have a month of upgrading software. For example, all the software that was used for landing has to be deleted, and new software has to be uploaded for you know, moving around a rover, and that takes a lot of time. The communications, while good, they're slow. Somebody compared it to the days that we had, you know, telephone hookup for emails. And you know how slow that is. Now here's a video that describes the helicopter, and I thought it would be interesting to know the details.
I'm at the Jet Propulsion Laboratory in Pasadena, and I'm here to see the first drone that's gonna fly on another planet. It's the Mars helicopter. Come on.
So this is our baby.
No way.
Yeah.
That thing right there is the actual machine that is going to take off and land on Mars. It's going with the Mars 2020 mission. That is the Mars helicopter.
This will be the first powered flight in another planet.
I mean, this is that. Now, it's necessary to say first powered flight because in 1985, the Soviet Vega missions deployed 2 helium balloons on Venus. They transmitted data for over 46 hours while floating at an altitude of 54 kilometers in Venus's dense atmosphere, which at the surface has a pressure of over 90 Earth atmospheres. In contrast, Mars has very little atmosphere, only around 1% of Earth's.
Flying this kind of a helicopter is equivalent to flying a similar helicopter on Earth at 100,000 feet. So you don't hear about many helicopters at 100,000. I think 40,000 feet is probably the record.
I checked. 40,000 feet is the record altitude reached by helicopters on Earth. 85,000 feet is the highest a plane has ever flown. On Mars, the air is even thinner than that.
Right, in terms of density, is 1% of what you have in this room. So in this room, a cubic meter of air is about a kilogram.
Yeah.
The same cubic meter on Mars will be about 15 grams to 18 grams. So that's
so you have to push a lot of air down.
Yes, you gotta get a lot of air flowing, and so the obvious trick, if you will, is to spin the blades faster.
It can spin between 2,300 RPM and 2,900 RPM.
That is fast.
That is fast, yes.
2,300. Here I'm trying to work out exactly how fast that is. So I looked it up, and on Earth, helicopters typically spin their rotors at around 500 RPM. So the Mars helicopter will have to spin its blades 5 times faster.
But there are some limits. You know, we really don't want to get the tips of the blades breaking the speed of sound.
Because then you have shock waves and all.
And you get all kinds of funky aerodynamics and transonic flows and things like that. So you don't want to go there. So we, in our designs, keep the tip mark numbers down to below about 0.7.
So 70% the speed of sound.
Yeah, so it's very conservative.
One advantage of flying on Mars is that gravity is only 38% of what it is on Earth. Even so, making the craft lightweight was essential.
Keeping the mass of this vehicle contained during the entire design process has been the major challenge.
Every single part had to be considered. The entire vehicle is less than 1.8 kilograms.
Whoa.
So less than 4 pounds.
That's about the same as this laptop.
The blades are foam core with carbon fiber layup. Each of them is about 35 grams.
Wow.
Yes, it's quite light, yes.
35 grams is the mass of 6 quarters. Think about that. 2 35-gram blades lifting an 1,800-gram helicopter by spinning 40 times per second in just 1% of Earth's atmosphere. How long can it fly for?
It's designed to fly up to 90 seconds.
A minute and a half of flight.
Yes.
To me, that sounds like forever. When you're talking about another planet flying autonomously by itself in 1/100th Earth's atmosphere, I mean, come on. Like, that's a long time.
It is, yeah.
One of the questions I had was, why didn't they use a quadcopter design? Well, because on Mars, the blades have to be so long that the whole craft would barely fit on the rover. 2 counter-rotating propellers provide the simplest design. They also generate lift more efficiently when stacked on top of each other.
The bottom rotor sees the more compactified flow. The top one pulls it, the bottom one sees sort of a more concentrated flow. Right. So the bottom rotor actually can do better than if they were separated apart.
But how do you test a helicopter designed for conditions on Mars on Earth? What would happen if you just took your Mars helicopter and you tried to take off on Earth?
It would just make a lot of noise.
Really?
And it probably wouldn't get to full head speed either.
Because of how much atmosphere we've got.
Exactly. It's like trying to swim in a thick soup. We have a really amazing chamber here on lab called the 25-foot space simulator. And in that chamber, you could simulate any kind of atmosphere you want. You can go to Martian pressures, you could stay at Earth pressures, whatever you want. But that only took care of half of the problem. That was the aerodynamics aspect of it. There's the other part, which is the gravity. We needed a way to fake Mars gravity here on Earth, and the best way that we could figure out to do that was a gravity offload. Gravity offload just means pulling up on the helicopter, so it only has to support about 38% of its weight, just like it will have to do on Mars. And effectively, it was a high-tech fishing reel. So taking a brushed DC motor, a reaction torque sensor, and a pulley, mounting that a couple stories in the air, and then attaching a fishing string to the top of the helicopter that would tug the necessary force required to offload the differences in gravity.
An actual fishing line?
Yeah, real fishing line.
But isn't that stretchy? Like, don't you want something that's perfectly rigid so as soon as you apply the torque, it gets applied to the craft?
Right. And we did a lot of testing with different vendors to find out which fishing line had the best spring constant for us.
What does the helicopter sound like? I imagined that in 1% of Earth's atmosphere, the helicopter would be pretty quiet.
Yeah, you're still at 1%, but it's still real loud.
Really?
Yeah, we have audio recordings of it too. But it's I would characterize it more like bah, something like that. When the gravity offload system was working and the chamber was pumped down, the helicopter thought it was on Mars. It felt like it was on Mars, the helicopter.
How do you actually steer this thing around and drive it?
So the way helicopters work is they have something called collective and cyclic. So what collectives do is they change the pitch on the blades uniformly. So throughout the entire revolution, if you move the collective, the blades will
change their angle of
change
attack.
your angle of attack, you'll get more lift. So that's basically what you would provide you heave control, right? You pitch more, you go up, pitch less, you come down. But then there's something called a cyclic on helicopters, which basically what it does is it modulates the pitch as it goes around. So it can pitch a little bit more here, less here. So it kind of like modulates. So what that does is it provides an asymmetric torque, right? When you're pitched up there, you get that additional torque. Now you get it, depending upon the stiffness of the system, you actually get it with that gyroscopic lag that can happen afterwards. So once you get an asymmetric torque, the vehicle wants to start pitching or rolling, right? So once it pitches and rolls, you're doing it stably, you are now pointed in a direction and your thrust vector now has a component that's horizontal in the direction that you pitched, right? So then you start translating in that direction.
I've heard that initially someone tried to fly it with a joystick?
Yes.
An early prototype?
If you were sitting right there on Mars and you were trying to joystick it, what is it like? And it's almost unflyable. And the reason for that, it's the aerodynamics of when you want to command a roll to the left, because you see yourself starting to move to the right and you start commanding a roll to the left, there's a delay aspect. So that delay effect makes it very, very difficult for a human to try and pilot it.
You can't fly this from Earth.
Because of the 20-minute kind of time delay, so you have to really send sequences.
So essentially, you're going to push a button, and like 20 minutes later, it'll take off and do its thing, and then you'll find out.
The way this flies autonomously, it has onboard gyros, onboard accelerometers, and onboard camera, and altimeter, and an inclinometer. And so using that sensor suite, real-time measurement, against the terrain and of course the gyros and the accelerometers sensing on board, the real-time estimation of the state of the vehicle is made continuously, again, hundreds of hertz. And then that's fed into the closed-loop control algorithm that takes the estimated state and then generates the correction that's needed at the blade level, and then the blades are continuously being controlled. So when you see video tapes of our successful flights, right, and the vehicle looks dead calm, is coming up and hovering and going laterally, coming back, the machines are working very, very fast and very, very hard. It just looks very calm, but yeah, so the blades are being continuously controlled.
That is amazing.
Yeah.
How will it handle a gentle breeze?
A lot of the movies depict
dust storms?
depict dust storms as being very aggressive on Mars. The truth of the matter is that 1% Earth's atmosphere is very little matter actually hitting you.
I mean, you're using that to lift yourself.
Exactly.
So obviously.
So there's enough to lift, right? But we also need to spin at 2,200 RPMs to be in the ballpark of lifting ourselves.
We built our own wind tunnel that we put inside this 25-foot chamber. How many fans was it, Teddy? 960 computer fans. So, but it did sound like a jet engine taking off. So we built a fan wall array. It's called an open cross-section wind tunnel, where you don't need the walls. Just the fact of having an array of fans, we are very confident of it being able to go at 11 meters per second. Even this vehicle, if I had known that somewhere along the way I'd be building a wind tunnel to do this, I would have probably not taken the job on, right?
How long does it take to recharge?
We recharge the whole day. So the whole day at Mars.
Right.
So
but does that mean that you could do one flight a day kind of thing, in theory?
In theory, yes. By design, it can.
What is the size of the battery?
Between 35 and 40 watt hours total.
That's equivalent to just 3 smartphone batteries. And get this, most of that energy isn't even used for flying.
It has to survive temperatures as low as about -80 to -100 degrees C at night. So we keep the batteries warm and we surround the batteries with our electronics board, so the electronics boards also stay warm. We take approximately 2/3 of energy just keeping things warm and warming things up to operate. Only 1/3 of the energy is available for flight.
Do you have insulation on there to keep it warm?
Yes. When you look at the helicopter, right, you have the solar panel on top with the antenna, and then next is the rotor system, and then bottom, what you see, this cube, is what we call the fuselage. You are seeing it now actually uncovered because you're seeing the last day of final, we're recovering, you know, for delivery to be integrated onto the rover. Okay, so usually you won't be seeing that. So the center of the cube is the ring of batteries, okay? There is space between the battery and the circuit boards that you're seeing, and then there will be a shell that we put on called the fuselage shell, and that will close like CO2, the gas around, and so the enclosure itself, we're using the CO2 gas as the insulation material.
Oh wow, no aerogel.
No aerogel. We did consider it was in the game. It was in the consideration in the beginning, and it turns out that just the CO2 as you know, insulator itself was sufficient for us to close our thermal model.
Right.
And so, guess why we wouldn't want to use aerogel if we have a choice?
Wait.
There you go. You're welcome to our team.
Now, before the helicopter can experience the frigid conditions on Mars, first it has to get there. And that's a reminder that not only is this an aircraft, it's also a spacecraft.
It has to survive launch. It has to survive launch loads, which, you know, easily exceed about 80 G. You know, because of the vibrational loads are 80 G.
Yeah. Then it has to survive the 7-month trip, complete with radiation. And finally, after pulling 9 Gs on entry into the Martian atmosphere, the helicopter needs to be deployed. This is going to be on the rover. Before you take off, does the rover like pick you up and put you down somewhere?
We're going to be stowed underneath the rover on the belly pan on our side. And there's going to be several sequences of firings of explosive devices to actually rotate us right side up and then drop us on the surface.
For example, the very last thing that the rover does is it's got us by this bolt, it's holding us, you know, about this high, and then it has to drop us, right?
Yeah.
So how do you undo a bolt on a spacecraft?
Just blow it up.
You blow it up. Basically, it's the materials, you know, undergoes a phase transition, which certainly increases the stress in the metal part of the thing and makes the bolt break. It's called a frangie bolt.
Then once we're on the surface, the rover drives over us. It gets about 100 meters away, and then we have about a 2-hour counter internally where we'll wake up after 2 hours, wait to hear some RF transmissions, and if we do get that link with the rover, then great.
Our base station on the rover would issue the fly now command. First flight will probably be a mutual selfie, you know, you would think. This is, after all, the selfie age. So
I like that as the goal of the first flight.
Yes, it is. In
Go
fact,
up,
no,
take
you know,
selfies.
the best time to fly this is at 11 o'clock in the morning local time on Mars. And the reason for that is we would have come out of the night where we would have spent a lot of battery power trying to, you know, stay warm. By 11 o'clock, the state of charge would have gotten to the point where we could fly without risking brownout on the battery and then, you know, dropping the whole craft to the ground. Also, 11 o'clock is where the sun would have warmed up things, so we don't quite have to heat up as much. And also, it's not late afternoon where, because of the warmth, the density has begun to drop, okay, and the winds have begun to pick up. Now, what we will investigate is after we get the first couple of flights under our belt, I'm sure we will try to fly in the afternoon and, you know, do more exploratory things. But the most conservative thing we can do is to sort of pick a mid-morning flight.
So what is the purpose of this mission? The Mars helicopter is first and foremost a technology demonstration to prove that we can fly on another planet. The helicopter can take color photos and videos, but its purpose is not to make scientific discoveries. Instead, it is to help engineers figure out how to design and build aircraft for future missions.
You can imagine something that's about 30 kilograms carrying, you know, a 2-kilogram science payload, doing exploration, acting like a scout, like a small vehicle like this, scouting ahead for some future rover. Or it could be a gadget that goes and picks up some kind of samples and brings it back to a central lander for more sophisticated analysis. Or it could be a completely standalone craft, and maybe more than one, that are exploring places where humans and rovers can't get to easily. So polar ice scarps, you know, sides of cliffs and so forth. So the real emphasis here is to try to get back all the engineering data so that it can inform that future design.
Flying on other planets will provide a new dimension in space exploration. An aircraft is faster and capable of covering more ground than a rover, and it can provide higher resolution imagery than an orbiting spacecraft. So maybe one day aircraft will be the companions of future rovers or even astronauts exploring other worlds.
Okay, but we're going to have to wait till April sometime before we know, how it flies and how it functions. But I thought this is an important new piece in exploration, namely being able to put up flying machines over planets. And by the way, the same design is planned for exploration of Titan, Saturn's moon Titan, which has an atmosphere as thick as Earth's. Of course, it's not oxygen and nitrogen. It's mostly methane, but airplanes can fly in methane, no problem. And so they're designing this for a mission in Saturn, which is going to be flown. I think they're talking about 2026 or something like that. So another program that I'm happy to do in a few years. Okay, well, let's continue.
Hey, George, one question, if I may.
Sure.
With all the dust flying around, do they have anything like a blower or something that things can dust themselves if needed? Because these storms can get particles to get in all sorts of joints.
Yeah, you're right. And I think there is enough wind that kind of blows them off. But just to give you, a point, Opportunity, which went dead because there was in winter time, there was some storms. Remember, there was global storms. I mean, Mars is smaller than Earth, and when they have these dust storms, they can be, global in scope. When spring came, Opportunity solar panels were full of dust, and therefore the batteries could not be recharged and went dead, just froze to death. So yes, that is an issue, and they have ways of getting it to blown off, but it is an issue on Mars, especially if you use solar panels, because solar panels need exposure, but then exposure means the dust can get on it. The vehicle itself, however, unlike Opportunity, uses RTGs for power, and that's not prone to dust storms. So, and I have some things on that too. So if we get, by the way, more engineering details. Okay, this is the engineering part.
Five, 4, engine ignition, 2, 1, 0. Relay and liftoff. As the countdown to Mars continues, the perseverance of humanity launching the next generation of robotic explorers to the Red Planet.
On July 30th, 2020, a United Launch Alliance Atlas V rocket lifted off from Cape Canaveral, Florida, carrying the next generation of Mars exploration vehicles, the Perseverance rover and the Ingenuity helicopter. And today, on February 18th, 2021, if all goes to plan, the two vehicles will land safely on the Martian surface after their long 7-month journey to the Red Planet. Only 40% of missions sent to Mars have been successful, and Perseverance will have to endure a vicious and complicated landing sequence as its creators wait, powerless to intervene, waiting for news of its success back in Pasadena. The Perseverance rover is the largest and heaviest rover JPL has ever sent to Mars, heavier than the Curiosity rover by 100 kilograms, and with that extra weight comes a whole host of new gadgets. This isn't some slightly upgraded version of the Curiosity rover. Perseverance is benefiting from almost 10 years of advancement of technology. It's packed with fascinating and novel technologies that will form a stepping stone in humankind's eventual first steps on the surface of the Red Planet. This is the insane engineering of the Perseverance rover. Perseverance, hopefully, is now safely on the ground, where it will live a long, illustrious life on the Red Planet. We have learned some things from the Curiosity rover that will hopefully help Perseverance avoid the struggles its predecessor is experiencing. We have made an entire video on the struggles of the Curiosity rover wheels and how they've been gradually falling apart on the harsh Martian surface. In the end, the engineers of JPL did not opt for shape memory alloy wheels like the ones we discussed in that video, but simply increased the diameter of the wheels, decreased their width, and increased their thickness, while incorporating sturdier curved threads that will better resist crack growth than Curiosity's sharp cornered threads. They have also foregone the rectangular cutouts which imprinted Morse code, spelling out the rover's origins in the rusty dirt of its new home. There is a whole host of new software upgrades too, like the algorithm that determines when to open the parachute. In the last mission, the parachute simply deployed when the target speed of 1,450 kilometers per hour was reached, after most of the hypersonic re-entry speed of 21,450 kilometers per hour had been bled off. For Perseverance, JPL wanted to increase the accuracy of their landing. So this time around, the chute will open when it is approaching the optimal trajectory for the landing site. It will also be scanning the surface of the landing site and correlating those images to its pre-existing map to allow the sky crane to choose the best landing site with minimal obstacles. Perseverance's ground navigation systems have also been significantly upgraded, with its optical sensors feeding data to a machine learning vision algorithm, allowing Perseverance to find its own path through the rough terrain of Mars, where Curiosity had to constantly stop and start with help from its earthbound controllers. Perseverance is benefiting massively from the past decade of improvements in autonomous flight and driving developed by the drone and automotive industries. This will mean Perseverance will be able to cover much more ground during its life, here in Jesuro Crater, a massive crater that was once home to a lake the same size as Lake Tahoe. You can see the remnants of this ancient river bed and delta spilling into what may have once been a habitable body of water. It is here that Perseverance will scour for signs of life. Before we get into all the gadgets it will use to do this, let's look at how Perseverance will power them. The Perseverance rover features the same radioisotope thermoelectric generator as the Curiosity rover. RTGs work by converting the heat from the natural decay of radioisotopes into electricity. It uses a simple principle called the Seebeck effect to generate electricity. The Seebeck effect essentially allows us to generate an electric current through a heat differential, as charge carriers, both electrons and electron holes, will move from hot to cold. So, if we have two semiconductors, one with charge carriers in the form of electrons and one with charge carriers in the form of holes, a potential difference between the two semiconductors will form when a heat gradient is applied. This potential difference causes a current to flow in the external circuit. These two semiconductors need to be both thermally insulating to ensure the heat gradient is maximized, but also electrically conductive to maximize the current. These two material properties are typically linked. Copper is both a great electric and heat conductor, while iron is a poor electric and heat conductor. Having a single material that is a great electric conductor and a poor heat conductor is extremely rare. For this reason, two unique materials are used for the P and N-type semiconductors: lead telluride for the N-type and an alloy commonly called tags for the P-type, which is formed from tellurinium, silver, germanium, and antimony. Now, we just need a consistent heat source. Thankfully, radioactive substances generate heat as they decay. The Perseverance rover uses 4.8 kilograms of plutonium dioxide as its heat source. This radioactive material primarily produces alpha waves, which is essential as this form of radiation is most efficiently converted to heat in a compact space. While plutonium-238 also releases minimal beta and gamma radiation, decreasing the weight of shielding needed to protect the electronics on board from these more powerful kinds of ionizing radiation, an essential characteristic for a lightweight spacecraft. The plutonium-238 is also formable into a ceramic-like material that will break into large chunks, rather than being vaporized and spread in the wind during a launch failure, where it could be inhaled or introduced into the food chain. The electricity this unit can provide will gradually degrade from its maximum of 110 watts at launch as its plutonium heart naturally decays, losing half of its energy every 87.9 years, which is much longer than the 138-day half-life of the early polonium-210 RTG prototypes. Another advantage of plutonium-238 for this application. This will power all of the instruments on board, like the MOXIE, which is one of the new devices I am most excited about aboard Perseverance. MOXIE is a new oxygen generation device that will test a vital technology for any future human mission to Mars. You may wonder, like I did, how is this different from the oxygen generation present in the International Space Station? There is obviously a limited supply of oxygen there. Why do we need to test this new technology on Mars, when we obviously have a tried and tested method of creating oxygen already, surely? The International Space Station does not really recycle oxygen. Oxygen is created on the International Space Station through electrolysis of water. This produces hydrogen and oxygen. The hydrogen is then reacted with carbon dioxide to form water and methane. The methane is then simply exhausted into space while the water is fed back into the system. The International Space Station requires regular resupply of water as we are losing 2 hydrogen atoms for every oxygen molecule we create. This is not a closed-loop system, and water is a pretty heavy material to be shipping to Mars. The Perseverance rover will test a new method of oxygen creation using this device, which will use solid oxide electrolysis to instead break the plentiful carbon dioxide in the Martian atmosphere into oxygen and carbon monoxide. Its operation is fairly simple. Air will be taken in through a dust filter by a specialized pump designed to be as light and compact as possible, called a scroll pump. Scroll pumps are pretty cool. They consist of 2 spiral scrolls, one stationary and one rotating. Air is taken in at the inlet here, and as the secondary scroll rotates, it traps and squeezes air against the primary stationary scroll. This continues to happen as the volume between the 2 scrolls decreases down the spiral, causing an increase in pressure. In this case, it causes the variable pressure Martian air, which is typically about 100 times lower than Earth's atmosphere, and compresses it to match Earth's sea level pressure. These kinds of pumps are lightweight, energy efficient, and reliable, making them the perfect air pump for the Perseverance rover. The pump feeds the carbon dioxide-rich air through a cell stack. Each stack consists of a catalytic cathode, a solid electrolyte, and an anode. As air passes over the cathode, which operates at 800 degrees Celsius, the carbon dioxide is split into carbon monoxide and oxygen ions, according to this reaction. The oxygen ion passes through the solid electrolyte to the anode, where it is oxidized, combining with a second oxygen atom to form gaseous O2, which is then passed out of the anode cavity and tested for purity. MOXIE can produce 20 grams of oxygen an hour. However, the unit will not run continuously, as it draws too much electricity, which will be needed for another operation. In total, the MOXIE system needs 168 watts, which is actually more than the 110 watts the RTG can provide at any one moment. So, this operation will need to be supplemented by 2 lithium-ion batteries that are included on board to make up for the low-power RTG, allowing it to store excess power during downtime. This device is exciting because it is a clear statement of intent. Oxygen is going to be a vital resource for any future mission. And this is actually a scaled-down prototype of the full-size version NASA eventually wants to send to Mars, along with an empty rocket. The full-scale version will produce about 2 kilograms per hour, which will gradually be stored inside the awaiting rocket over the course of a year and a half, providing life-sustaining air for any future human missions and the oxidizer needed for the ride home. The next device, which is also depending on a future Mars mission to complete its purpose, is the core sampling drill. The Curiosity rover sampling system drilled and scooped soil into this instrument, the SAM, standing for the Sample Analysis at Mars. The SAM is located here on the rover. It contained multiple tools that would be commonplace in many Earth-bound labs: a mass spectrometer, a gas chromatograph, and a tunable laser spectrometer, each looking for different signs of life on Mars. Perseverance has replaced the space this unit took up with a totally new system, the Sample Caching System. The robotic arm of the rover features a coring drill, which will cut out cylindrical core samples from the Martian surface. Once collected, the robot head mates with the drill bit carousel, where it transfers the bit and the sample tube into a rotating carousel that takes it to the belly of the rover, where another robotic arm resides. Here, a number of operations takes place. First, the arm pulls the sample tube out of the drill bit and takes multiple images of it, before and after calculating the volume of the sample. Then, it stores it in one of the 42 slots under the belly of the rover, where they will remain until the rover deposits them in these sample tubes at a designated caching spot on the surface of Mars. This is where things get really interesting. There are plans to send another rover, designed by the ESA, to Mars in 2026. This rover will deliver the samples back to its NASA-designed lander, which will load them into a Mars Ascent vehicle, blasting the samples into orbit where an ESA Earth return vehicle will be waiting for it. We are attempting to bring soil back from Mars with robots. If that isn't insane engineering, I don't know what is, and we have barely scratched the surface of what this rover is capable of. There is a whole host of new sensors on board that do not require Perseverance to collect soil, each using different forms of electromagnetic radiation to investigate the ground below them. The Sherlock instrument on the robotic head will look for signs of biosignatures using Raman and luminescence spectroscopy, which both detect molecules based on how they interact with UV light. It will sit about 5 centimeters off the ground, where it will focus its UV laser onto the soil and be able to detect chemicals that would indicate the presence of past life. The rover also has an X-ray imager called Pixel that will be able to visualize the texture of the ground below it, looking for tiny variations in geology that would indicate that microbial life has altered its environment, while also being able to detect chemical compositions by observing the fluorescence of the target under X-ray electromagnetic radiation. There are several other sensors, like the ground-penetrating radar imager located at the rear of the rover, which will give us visualizations of the composition of geology up to 10 meters under the surface, and possibly even identify water resources buried below, a vital resource for human missions. These are just some of the sensors on board, and of course, there are the usual high-definition color cameras that are going to send back amazing images to Earth, and this time we included a microphone, so we'll be able to hear what our future life on Mars may sound like. It may even catch the whirring of helicopter blades off in the distance, because by far the most exciting part of this mission, to me, is the Ingenuity helicopter. After all, if successful, this will be the first time humans have demonstrated controlled, powered flight on another planet. Powered flight on Mars presents many challenges. The atmosphere is about 1% the density of Earth's, meaning there is less air to push down to achieve lift. To combat this, the propeller blades, which are counter-rotating to eliminate the need for a tail rotor, have to spin much faster than a traditional helicopter blade at about 2,400 RPM.
Okay, the rest of the video talks about the helicopter, which we already covered in a previous video. But I think, it gives you a good example of the details that have to be thought of before launches are made. And I'm just, as a physicist, I'm just excited about the detailed engineering that had to go into every single question that you could possibly come up with and have a solution for. Now, a little bit of Mars Digger. We had, if you remember, Mars Digger that was launched about 1.5 years ago. Unfortunately, it wasn't able to perform as they wanted to drill as far as 16 feet into the Martian soil. It was designed by a German firm, and they thought they had everything worked out. Unfortunately, it wasn't because of the viscosity and the powder of the soil. It couldn't drill more than 2 feet. So that they put it to bed, but it is taking photos and it is doing scientific work. But the original intent of it is, I guess they terminated trying to dig any deeper into it. Curiosity is doing very well. It celebrated its 3,000th day on Mars. And I think it's going to continue being, giving us a lot of good material. It is located about 1,000 miles away from Perseverance, so the location is different. By the way, you heard about the local time of 11 o'clock for launching the Endeavour, the helicopter. But remember, 11 o'clock Mars time is different than 11 o'clock California time, because Martian day is 24 hours and 40 minutes. So every day it shifts. So that means if people who are working on Mars time have essentially adjust their living to Martian time, which shifts every day by 40 minutes. And so there's actually another video that describes people, family, living on Martian time, because in order to be, to work during the daytime on Mars, it can be daytime here on Earth at some point of time, but every day it shifts by 40 minutes. So it's almost a little bit, comical how the children describe their Martian day living on Mars. This is give you an idea of the photos that are taken. They're down to the point of being able to measure half an inch easily. And so very detailed, almost microscopic detail of soil can be measured and diagnosed. Okay, I think it completes the presentation. I would be amiss, however, not to mention that we have other countries competing for Mars. United Arab Emirates launched a spacecraft that is now circling Mars, and it succeeded in being put in orbit. And its mission is basically to observe the surface. China, on the other hand, has another mission to Mars. Their mission is to actually land a rover. Their spacecraft is now circling Mars, and probably around April, they plan to land the rover. And as usual, China doesn't really disclose much what is going to happen, but people think that they're trying to catch up with the US, although they have a long way to go. But they're obviously able to not only launch, but succeed in landing craft, as they have a rover on the moon right now as we speak.
Can you give more detail, or do you know more detail of how they're going to go about trying to determine whether there was life on Mars? I know they're going to look for geological formations that would have been there by life forms moving over the surface, but I'm wondering if there's anything more that you can shed light on how they're going to go about doing it.
Well, they're assuming that if there was life, it would be microscopic. And so there are examinations of microscopic remnants on the flat, of the lake, the bottom of the lake, which is now dry, to see if there are any, I don't want to say skeletons, but there's very nutrients that are biological in the origin. But it's if there was life several billion years ago, the question is, what are the remnants of it? It'd be great if they could find a skeleton of a dinosaur, but I don't think that that's going to happen. Although, one of the things is there's a major canyon that covers probably a good portion of Mars, bigger than the Grand Canyon. And if we can get a helicopter to fly inside that, that would be a very interesting thing, because, the idea is maybe there was some remnants of life in the caves, and you could find the caves in the canyon, where, of course, the pressure is higher and the density of air is higher.
Do you know if there's nitrogen been found on Mars? Because nitrogen's found in all life forms on Earth.
There is nitrogen. It's not as abundant, but it's mostly carbon dioxide and nitrogen, but very little oxygen. That's why they're talking about creating oxygen from carbon dioxide.
Right. Thanks.
I think what they're looking for is small molecules, which are combinations of nitrogen and carbon, which are not found at all ever in nature, but are found in life forms all the time. And those are relatively stable. That's what they think they're looking for. Personally, I don't think they're going to find anything, but that's what they're looking for.
Well, as they say, if you don't look for it, you're not going to find it, right? So
that would be exactly my approach.
Take care, everybody.